Okay, can you hear me? Good morning, everyone. Apologies for starting a few minutes late, but I can't quite master the microphones on the table, so this feels slightly too formal, but this is how it will have to be. So welcome, everybody. It's great, absolutely great to see such a good turnout. My name's Alan Cook, and I'm the chair of Action for ME, and I've been the chair for about 3.5 years now. So in my time here, we've been sort of seeking to professionalise the charity, make it a bit more statesmanlike, if you like, and also make us much more transparent and accountable to the membership. We've done a whole variety of things like all trustees are now formally put up for election amongst the membership and voted on. Their terms of office are restricted to 3-year terms, which can be renewable. We issue Sonia, you could wave it, a rather splendid annual report, which I think outlines all the things that we, which you can't find it, that we can't give out, that you'd hopefully have a copy of, which just demonstrates what we've achieved during the year and how we're developing. And finally, we have a public AGM. So 3 years ago, we had a go at an AGM, and we did do it here, but there was no point in doing it in this room because there was only most of the trustees and 4 attendees. And one of those 4 I've been chatting to this morning. We have come a long way. I knew it would take time to build, but I thought it would take longer than 3 years. But frankly, of course, we are cheating because what we've done is to lure along illustrious researchers to talk at the event, and then we've killed 2 birds with 1 stone by having a strong research-oriented agenda, which people would probably come to in their own right, coupled with the AGM. Now, the components of the AGM, frankly, are not fantastically interesting. They are about transparency and governance, but the only really interesting bit of the AGM is when the Chief Exec stands up and says what she's done in the last year and what she's planning to do in the next year. So what we've done is taken that out of the AGM slot and putting it in the appropriate part of the day, as you will see. So we have what I think is a really interesting agenda. We'll take Sonia's slot at the appropriate stage. And when we get right to the end, which is about 3:20 to 4, we will do a very short, sharp and AGM. Now, I have already told you it's not fantastically interested, and I just want to implore you not to all run off just before it starts, because otherwise we don't actually get to vote on the accounts and things like that. But it will be short, sharp, and it does give us an opportunity to relate slightly more formally as to what we're doing with the money that people do put forward. I know a number of people will be arriving during the day, and some have to leave afterwards, so don't be too disconcerted if you see people coming and going. There's a few housekeeping things that I have to say. There is no plans for either a fire alarm test or a fire. Right. So if the alarm goes off, I suggest you move pretty quickly. There will be people here in high visibility jackets and hard hats that will show you the way out. We have rest areas on the far corner to my right, back there. We have a relaxation room with sofas and mats and whatever. If people find this is all a bit too much, then in fact we have a talk later on sleep, don't we, Jason? And that may induce you to go in there then, we'll see. There are feedback forms in your packs, I'll remind you at the end, but it would be good if you could fill those in. It sometimes helps, I find, if you fill them in as you go, which is why I'm mentioning it now, because when you get to the end, you have difficulty remembering the strengths and weaknesses of the different slots. And you'll have seen a note on the door saying that we are filming the event. If anybody has a problem, we can let us know, and we can make sure we accommodate that. But it is quite important for us to be able to put the wise words that are likely to be uttered up on our website during the course of the day. I did say that we do feel very accountable for the money that people do donate and subscribe to the organisation. So as such, we have been very careful to make this as cost-free an event as we can. So gratitude goes to Alan and Overy for supplying all the facilities, the support, the security, and to KPMG for supplying the catering at lunchtime or whatever. It's just amazing if you have some mates what you can get away with for a good cause. So this will be running from Action from MB's perspective at zero cost, thanks to them. So I think really that gives me that completes all the sort of introductory things I wanted to say. I do want to make sure there's enough time for interaction if people have got questions. So you have a timetable before you. I hope you will give me the permission to vary it slightly depending upon the level of interest on topics and what people have to say. I do promise, though, we will get to 4 o'clock having finished at the very latest. So we'll get to the right end time, but we might want to have some flexibility during the day depending on what piques our collective interest at different times. So we're going to start with our keynote speaker. I told him we'd only got good numbers because he was here. He tried to look abashed and deny that, but I'm sure he was pleased that I said it. But nevertheless, we are very, very delighted to have Stephen Holgate, Professor Stephen Holgate, with us. He's the Medical Research Council Clinical Professor of Immunopharmacology at the Faculty of Medicine in Southampton and Chair, not quite importantly, of the newly formed UK CFS ME Research Collaborative. It's a big word, that, collaborative. In fact, the other one was quite a big word as well. But collaborative is a bigger word because it means a lot, I think, for this sector to see efforts being marshalled together for maximum effort and maximum effect, both amongst the medical charities, which Sonia will talk about a bit, but particularly now on research, where we can be sure that if there is money available for research in a coordinated way amongst the research community, we can identify what are the best causes, where should we go next on the search that we've set out on. I mean, now he's published nearly 1,000 peer-reviewed papers and has led significant developments in the respiratory field. And we're really lucky to have him as a member of our own Action for ME's research panel as well. So Stephen's going to give us a presentation on the developments in ME research, and afterwards there should be time for a few questions. Thank you, Stephen.
Well, thank you very much, Alan, and thank you for the privilege of coming to this amazing building. I thought Action for ME owned this building, but I've been told otherwise. But it is very kind of the owners to let us use it like this, and it's splendid. I was asking Sonia what the magic trick was, because I wouldn't mind coming here on other occasions. But anyway, it's lovely to have such a super audience, and as Alan says, I mean, to think that a few years ago you just had 4, and now we have all these people interested in this condition. And rightly so, because it's one of the enigmas in current medicine that we're all trying to grapple with in our own ways to understand and to help patients with it. And I think today you're going to hear some exciting research activity, and I suppose it's my role to help, in a way, set the scene, really. And I'm going to do this in 3 ways, and forgive me for doing this, but I'm not going to go straight into ME and chronic fatigue syndrome. I'm going to, first of all, talk a little bit about where medicine came from and how it's evolved over the last century to where we are now. I'm then going to talk about some of the exciting new things that are happening in medicine that are opening up very complicated diseases that we had no insight into previously. And then I'm going to try and demonstrate to you that because of that, we've got a unique opportunity now in this condition. So if you'll bear with me as I go through those different components, I'd be grateful. First of all, the condition. The condition is common, as you all know. It's disabling. Treatment at the present time is only moderately effective, and you may argue about that one way or the other. And research has proven to be extraordinarily difficult. In other words, if we look back over the last 2 decades, the amount of research that's contributed to patient benefit is actually quite small at the end of the day, and that's disappointing in any aspect of medicine. If we look at the description of the condition on the right there, you can see that it captures a number of different organs from the brain downwards, really, and there's hardly an organ not affected by this condition, which in a way creates the complexity that many patients have to grapple with. So that's the problem. The perception is also interesting, and when I came into this field about 4 years ago at the Medical Research Council, it was really quite a difficult time because the Medical Research Council was supporting almost no research in the area at all, and there was a sort of standoff really between the MRC and the community out there as to how things were going to progress, and things were going nowhere quite quickly. And I think part of the answer for that lay in this particular slide, because it's about perception, really. And this was a little survey that was published in the Journal of the Royal Society of Medicine, where people asked different organisations what their perception of ME and chronic fatigue syndrome was. And you'll see there, looking at those 3 different agencies, ME organisations like this one, the media, the newspapers and so on, television, and the medical agencies like the MRC. And you'll see there are widely different concepts, widely different. And of course it's that huge difference in how the disease is viewed that has created a lot of the problems that we're all grappling with in research, and that patients are grappling with in terms of getting proper medical care because of the misconceptions that have grown in different communities. And a lot of that is around ignorance, the lack of knowledge about what really is driving the disability and symptoms in this group of conditions. So there are disagreements, not only over just defining it, and every year there's another attempt at defining it, and we've just heard that the United States are about to set up another group at the National Academy of Sciences to have another go at defining it, which will hopefully be helpful. But also the causes, mechanisms and diagnosis, and this is where all the controversy lies. So we haven't got much substrate to work on here in terms of the knowledge base upon which to build our understanding. And I was fascinated, Sonia, in your annual report, when you did this survey, which I'm sure you'll talk about later, when people are asked about what their patients are asked about what their expectations are in terms of their own disease. We get these extraordinary statements about almost a desperate plea, really, for the research community to get their act together and start finding out what the heck's going on here. And I don't need to go through those, and I think you just selected a handful. I'm sure there were hundreds of others very similar. And I don't think it matters really what they say, because I think all of those come up with the same message, that we are bathing in a bath of ignorance in this condition at the present time. And times have got to change if we're going to really make inroads into this. So how can we make those inroads when all these symptoms that patients have, which vary enormously from patient to patient, age, gender, precipitating factors, factors that make it worse, how are we going to gain insight into this? Well, I live about 3.5 miles from where Florence Nightingale was buried, in a little village called East Wellow. She was an extraordinary person, as many of you know, because during the Crimean War she transformed the way nursing emerged in this country, and there's a picture there of her on the wards in Scutari. The East Wellow Church, where she's buried, is shown in the bottom right-hand side. That photograph was taken in 1911. And you'll see on her grave, FN, she never wanted to be acknowledged as an individual who attracted attention to herself. And when she turned out for her funeral, there were nearly 5,000 people lining that little road there, but only 12 people in the church, because she only wanted her close family. And she was an amazing person in many respects, and all of us associate her with St Thomas's Hospital and the nursing traditions, many of which I think the NHS might have forgotten in recent times. But it is interesting to note that when she returned from the Crimean War, she developed symptoms that were almost identical, really, to chronic fatigue syndrome and ME. And I needn't read that out to you. You can read it for yourself. She didn't waste her time. In fact, she became a mathematician and a statistician, and she was one of the first people to actually put data into a visible form in presenting it in terms of bar charts and Venn diagrams. But, of course, her life was terrible because she was not able to leave the house, basically. And many of us recognize that in this condition. At about that time, medicine was undergoing quite a change. There was one man in particular who was leading this charge, and really I would put at his feet the origins of the science of medicine. Because prior to the sort of late 19th century, medicine was largely a magic art. There were only 3 drugs available, and most of the rest of the treatments were all concoctions from various extracts. And surgery, of course, was absolutely primitive. And William Mozilla, who is the man I'm talking about, was trained in Montreal in Canada, and he was an incredible visionary at the time. There's 2 little statements there that I'd like you to read in the italics. I won't read them. But what he basically says is if you're interested in medicine, you've got to be interested in patients, because that's what medicine is all about. And what's also interesting is that for the first 3 years after he qualified in medicine from the medical school in Montreal, Canada, he went to Philadelphia and worked in the death rooms in Philadelphia, learning pathology. Now, can you imagine what that must have been like in the late 19th century, where there was no refrigeration, and it must have been absolutely appalling. But he spent day after day after day trawling through the deaths in that city, trying to understand what was going on in disease, because patients were at the center of his heart. And this was the man who then went off to Baltimore to set up a medical school called the Johns Hopkins Medical School, which probably is one of the top 3 medical schools in the United States. There you see a painting of him with the 3 other co-founders of the medical school, and you'll see that in that little picture, his first, or their first graduates that came into medical school back in 1889. And of course, that medical school was built on the principles of Osler. And those principles of Osler were really all about the principles and the practice of medicine. And the first textbook which he published on this in 1892, which has gone through 46 revisions since then and is still published, is shown there. And there he is writing for his textbook. And at the age of 59, he left Hopkins and came to Oxford and was the Regius Professor of Medicine in Oxford and influenced British medicine enormously for the latter part of his life. What was so magic about this man was that spending this time in the death rooms in Philadelphia led him to think differently about disease. And what he did really was combine his understanding of pathology and symptoms and signs of disease with the physiology, that's the working of the body, which in those days was quite primitive, but there was some knowledge, as well as the emerging chemistry and physics that were coming into science in the 19th century, if you recall that time. And Faraday was inventing electricity and the battery and all of that to come up with this extraordinary textbook. And if anybody's ever got the chance of just looking at some of his writings, it is amazing what he was able to do in 1892, coming up with this amazing textbook of medicine. And that served us really for over 100 years, 150 years almost. And it's based really on observation of what patients, their symptoms and their signs, and also on pathology. But we're in a very difficult situation in medicine now, and many of you will know this because you pick up a paper every day and you'll read about it. We've got intractable health problems out there. The reductionist models, X plus Y equals Z, the simple cause of a disease, have largely been mined by therapeutics or by surgery. We can treat simple things quite well. But it's the non-communicable diseases which are really the issue now. The degenerative diseases, those that are associated with our modern lifestyle, and the inflammatory diseases, the chronic inflammation. And I would put dementia in this category just as much as I'd put rheumatoid arthritis. And so after this extraordinary 130-odd years of medicine improving, we're now facing an amazing problem. Our lifestyle has become such that we're looking at a public health in the next 50 years that doesn't look too rosy unless something changes dramatically. And I've listed a few things there that may be driving it. And some may even consider this as a bit of a medical time bomb, especially if you look at the children out there at the moment who spend their life on computers, who are frightened to go outside more than 30 yards beyond their own house, whose diet is mostly made up of carbohydrates and manufactured foods, and whose social contacts are now limited to surrealistic contacts through the internet. So this is serious. And then, in addition, we've got the industry out there that makes treatments for us failing in a spectacular way. And the problem with it is that the ability to find new drugs, like cholesterol-lowering drugs or antihypertensives or diabetes drugs, the easy ones have all been found. We're left now with expensive, difficult research. And if, again, you can't pick up the newspaper without looking at the sheer cost of drugs these days for development and the anxiety that creates in the patient population. If we just look at the industry for a moment, it takes something like 10 years to develop a drug from its concept to the final compound. Of a drug that reaches you as a patient, or our patients, often start off as 5,000 or 10,000 different chemical entities. And the wastage over that 10 years is enormous. And then it has to go through all these different processes before it's approved so that it's safe and effective. And this now costs not $1 billion, $1.4 billion to produce any single drug that gets out there. So this is an issue, and the business model is non-viable. So there are the problems. But set against this, we've got some fantastic things happening out there. We've got this new technology, which is absolutely transformative, and I'm going to go into that in a moment. We've got new ways of applying Florence Nightingale's approach to looking at complex data sets, statistics, as it's commonly called. And we've got new mathematical ways of looking at whole populations now and picking out of those populations disease trends and disease processes that gives us huge insight into underlying mechanisms, especially in response to the environment. But of course things continue, and yesterday you'll have heard that Novartis is moving out of Britain and going off to Boston and India. They're closing the centre in Horsham. We've already lost AstraZeneca. Glaxo is downsized by 30% in Stockbridge, and of course Pfizer shut in Sandwich. So these are major pharmaceutical companies that are really dying on the vine because the model is no longer serving the people for which these drug companies were set up for, to discover drugs. So there's an important issue for us to face. Another incredible change that's happening out there is the way that individual patients now are positioned within the healthcare paradigm. I mean, in the days when I was brought up as a medical student in London, we were told information, we transmitted that to patients via general practice or by specialists in that sort of rather linear way. Well, the internet in particular has created a completely different paradigm now, and so often doctors are faced with a situation where a patient comes much more informed than they are about the disease. And I think your area of ME, chronic fatigue syndrome, is a good example of that. So often doctors can actually feel somewhat threatened when somebody comes forward with a fistful of information that they know nothing about. So this really is a major difference that has to be appreciated. And furthermore, we're getting vision now that rather than treating diseases as separate entities, we've got to treat whole pathways of patients over time. And the way primary care is going these days, it's not becoming less fragmented, it's becoming more fragmented. So being able to do this, treat patients as a whole, is becoming much more difficult. So let me get into the science a little bit and say why I think it's worth fighting our corner here and really trying to get ourselves out of this rather difficult situation. And it's all around understanding how cells work and how biology operates and the extraordinary things that have happened these last 20 years. Now, we know that cells obviously are made up of a bag of proteins, and those proteins create what we call the function of cells, and then the cells themselves make up organs, and then organs work together to create a body. But what's happened really is that the biology behind all of that has now been carefully worked up and analysed to a point where, for the very first time, it can be harnessed as a whole, i.e. not just little bits of it, but the whole thing looked at. So we can look at genes, which tells us what potentially can happen to a particular person. We can look at what's called a transcriptome, which is the message that comes out of the gene to the next stage, which tells us what appears to be happening, but it may not be happening yet. Then we look at the proteins that those genes make, which tells us what makes it happen. And finally, we can look at the products coming out of those cells that tells us what is actually happening. Now, all the technology now is in place to do that whole journey. And the reason it's in place is because technology, which has its origins in this particular part of London here, the city, and adventure and entrepreneurialism, has meant that these very, very expensive technologies are now can be done at prices that most of us in technology can afford. When the first genome was sequenced, and we're talking here about just under 20 years ago now, 18 years ago, it cost $23 million to sequence one person's genome. Now, as I heard just last week, it costs $940 to do the same job. Now that is an extraordinary change. So suddenly the human diary is open to everybody to be able to read, which of course at $23 million for each one you'd never be able to do. And this is one of the great breakthroughs that's enabling all of this. And that's happening across all of these technologies. And so what is this doing to healthcare? Well, what it's doing is that we can look into the genome in a very precise way, because it is the diary of everybody, and enables us to look at how those genes are able to translate themselves into human disease in that person. And we call this personalised medicine. And this is a definition that came out of the National Academy of Sciences in the United States. It's just a description, but it's all about precision. It's all about understanding the biology that the genes are able to translate to create a set of circumstances that lead to either health or disease in a particular setting. And to be able to apply this, one doesn't need to just be able to understand the genes and the proteins that are produced, but one needs to be able to obviously pick up tests that we can use in a clinic to be able to identify this easily. You don't want to be able to sequence the whole of a human genome to be able to get the answer. So this is where we are at the present moment. Some people call it P4 medicine. Now this is the next Osler. This is the personalised, the predictive, the preventative, and the participatory, or participative if you're American, medicine. Now, going back to Osler again, and where I came from in medical practice, we were taught pathology, both gross pathology and down the microscope, and of course this is how we diagnose disease, looking at the cells under the microscope like this man is doing here. But let me just take an example. If we take something like breast cancer, okay, which most of you are very familiar with, then breast cancer used to be treated with one size fits all, that you had a treatment, either radiotherapy or some cytotoxic drug, and you know, it was a bit of chancy whether you responded or not to it, and if you did respond, that was great. If you didn't, bad luck. There was nothing you could do about it. But since this new medicine has come in, cancer in particular, and I'm using breast cancer as a simple example to start with, provides an opportunity to look at what the individual cancer of that human being is actually doing to direct the treatment individually to them. So in the old days, it was one size fits all. Okay? All cancers were the same. All cells in cancer looked the same. They were treated with the cytotoxic drugs. And what's happened in the last 15 years or so is that we recognize in cancer that breast cancer, for example, there are multiple forms of it. And lower down the microscope, it all looks the same. There are, in fact, now up to 15 different subtypes of breast cancer based on different mechanisms. And they can be identified by the molecular signatures that are in the cancer cell, by understanding how the genes are changing the proteins that are making these cancers behave differently. So rather than one size fits all, we've got these 15 different breast cancers now. Well, can we do anything about that? Well, yes, you know what the abnormalities are, then you can target the treatments. And this is a fairly simple model, but obviously you know breast cancer can be treated by blocking the estrogen receptor with tamoxifen, and obviously those that have high expression of these receptors are the ones that are most likely to respond to that treatment. And in those patients, it's incredibly effective. But there's no point in giving tamoxifen to somebody who's not expressing high levels of that receptor, because it's just not going to work. So you understand the biology of the response. Another treatment is an antibody that neutralizes a growth factor receptor, and it's called HER2. And this growth factor receptor makes the cells divide, and by blocking that receptor or by activating an immune cell that attacks the cell, the cancer cell, through that receptor, with this antibody, you can kill the cells. So you can profile this type of breast cancer by finding this receptor on the cell surface, the HER2 receptor. There's no point in giving this expensive antibody to people that don't express the receptor, because it's not going to work. So that's the principle of all of this. Now let me take something else. Pancreatic cancer, which has 100% mortality almost. That's about 96%. Huge progress is being made in pancreatic cancer now. Now you can't see what's on those blobs. It doesn't really matter. But those blue blobs represent the different pathways coming out of the genetic analysis of the pancreatic cancer cell. And what's exciting is if they take one patient, the green one there, and they look at which pathways are involved, they're able to find these 12 pathways or 15 pathways in the green, which are causing that cell to become cancerous. But then if they take a second patient sitting in the bed next door, and they take those cells, and they do exactly the same analysis, an entirely different set of pathways come out, the ones in red. Totally different. That under the microscope, the cancer looks identical between these two patients. So are you going to treat them the same? Well, clearly not, because the causative mechanisms of the two diseases are quite different. And so now in the whole of cancer, and this is just one example, lung cancer is another, which is making huge progress, we're being able to cut up or salami slice the cancer into these treatable bite-sized pieces where the treatment targets the cause of the disease. This was a paper published in Nature about 3 weeks ago. So here we are, we're getting quite up to date now. They looked at 11,000 different cancers from different patients. And along the top there, which you can't read, are 29 different cancers. Kidney, brain, lung, whatever. Leukemia, the lot. On the vertical axis, coming down here, the green blobs represent a particular pathway that's abnormal. And you can see as you go across those different cancers that abnormal pathways are shared by different cancers. So you might well ask yourself, well, what's the point in going to a lung specialist or a gastric specialist or a brain specialist if the same pathways are being shared by different tumours? And so oncology, that's the treatment of cancer now, is very much targeted about identifying these pathways and directing the therapy to restore the response of the pathway so the cell is killed. So this is a transformative change in the way we're treating cancer. I mean, it's making a huge difference. So I've had the privilege of working in Europe to try and build up this whole principle across Europe, including the UK, to get this personalised medicine into the health services of different providers. And it's called the European Science Foundation Forward Look. And it doesn't really matter what the conclusions are. We had 80 recommendations and they're being picked up by various organisations. But the key to this is the centre of that diagram. You see, this is all about the individual citizen. This is not about herds of people receiving the same treatment. And of course, as a result of that, and these new pathways, we're going to get new diseases coming out. So breast cancer is not going to be one disease anymore. It's going to be 15 different diseases with different treatments. Likewise for some of the other cancers. And we're going to get a new description of disease. And if we extrapolate that to rheumatoid arthritis, to dementia, to osteoporosis, and all these other conditions, you can see that we're going to have quite a complicated set of disorders where the therapy isn't going to be the blockbuster drug, it's going to be tailored to the abnormality in the individual. So if this is right, and if we're able to do this with modern technology, then we're going to get better medicines. They're going to be safer because they're targeted to that one particular activity. As a consequence, they'll become cheaper because they'll be more effective. We'll get a better health care because we won't get all the side effects and all that stuff that we have at the present time. And hopefully we'll get less disparity in the healthcare system. So I'm a chest physician, okay? And this is an area I spent my life in. Now let me just give you one example and to show you how amazing this is. Now this looks an awfully complicated slide. The molecular revolution has enabled us to understand what the abnormality in cystic fibrosis is. And what happens in cystic fibrosis, as you know, is that the lungs fill up with mucus and people die, usually of lung infection, but they can also get mucus in the gut and in the liver, which causes similar problems. And the abnormality lies in the ability to transport water across the epithelial membrane through this so-called chloride transporter, and that's a picture of it here. Because it was understood what the nature of the lesion was in cystic fibrosis, genetic understanding found 1,000 different mutations that could go wrong in that particular receptor. 1,000. So here we think of cystic fibrosis as a single disease. We've got 1,000 mutations that contribute to the cystic fibrosis. Fortunately, the really damaging ones are in about 7 mutations, so the rest of them just colour the intensity of the disease. But one of them, which is a mutation which is close to that little pocket over here on the right, is one where a drug has been able to be developed and to restore the function of that receptor to normal. So that receptor then functions normally. Now you may think, oh, well, 4% of the CF patients in the world have that, so it's very uncommon. I can tell you, if you're living in Ireland, it's 23% of cystic fibrosis patients have this genetic lesion. And on the top right-hand side, the drug that they've developed, which is called VX770, when given, within 10 days of giving this drug, these children are normal. Now, can you imagine as a parent what that feels like? Your genetic abnormality, devastating prognosis over the next 30 years, and somebody comes along with a drug and you can transform a child's life. And that's what's happening here. And it's not just happening with this, it's happening in muscular dystrophy and other areas too. So understanding the biology is getting this extraordinary ability now to be able to be precise in terms of restoring response. Now, complex disease is going to be like a series of rare diseases at the end of the day because of these different pathways in different patients. And this is going to lead to a different way we actually describe disease. So breast cancer won't be breast cancer anymore. There are 15 different subtypes. and they'll have different names probably according to the abnormality. But it'll be the same in rheumatoid arthritis or the same in dementia. There'll be different disease subtypes. And the United States and here at the Academy of Medical Sciences in the UK, we're grappling with this in terms of what it means for healthcare. Because the ability now to capture this biological information is being coupled with the ability to interrogate whole populations. So if you take Scotland as an example, the whole of that population has its medical records being carefully recorded. And those records are in GP, in hospital, prescribing, whatever, are being interrogated to look at different disease subtypes on a population level. So these observational studies, which is what we call those, epidemiological is another word you can use sometimes, plus this biomedical revolution will lead to this knowledge network, this incredible knowledge. And this knowledge will be interrogated to come up with new descriptors of human disease, the new OSLA. That will give us new diagnostic tests, which are very precise, give us new treatments and new health outcomes. That's the prediction. This is where we are. So I chair the Access Committee of something called the National Phenome Centre at Imperial College. They were given equipment from the Olympic Games that they used to analyse drugs in blood and urine during the Olympics, to analyse the results of stratification of complex diseases. And this equipment, which is shown here, is in Imperial College in the Hammersmith and in South Kensington. The technology is amazing. They can look at simultaneously, something like 15,000 chemical compounds being generated by a single biological sample. Simultaneously, almost instantly. In fact, so much so that Jeremy Nicholson, who runs this unit, is using a surgical knife now and analysing the smoke that's coming off the cautery knife to tell the surgeon in brain tumour excision whether they're excising the tumour or not properly, because the smoke has got different chemicals in it that are instantly being analysed. Okay? And this technology is doing that. That's where we are. It's amazing. Absolutely amazing. The challenge, therefore, isn't the technology. The challenge is how we integrate this technology. So we're getting the patient records, we're getting the clinical descriptions, we're getting all this exciting new data from looking at the molecular expression from DNA right the way through to cell function and physiology. But it's how we take all these layers of data and put it together for a single patient and make use of it. And that's really where the mathematics comes. That's where the new revolution is coming from. And just as OSLA connected pathology to clinical observation, what we're now doing is connecting mathematics and physics and material science to biology. That's where the revolution is. Because this revolution really is about interrogating all this amazing information that we're collecting. And of course, the computer world, the IBMs, the Microsofts, the people who develop the technology for this are also exploding, and there's hardly a day goes by you don't hear something about these incredible companies. And we have the ability to store data now from all these different ways of capturing knowledge about a disease in the cloud. I mean, we can store large amounts of information. So this now is in place as well. But our collaborators now are not pharmaceutical companies, they're IBM, they're Microsoft, they're Cambridge Computers. They're a different group of people altogether, just as OSLA when he was doing his pathology. And this is Leroy Hood. He works in San Francisco. He's very much into all of this integrated science. And he talks about the holy trinity of biology changing as a result of computational and mathematical tools. We are understanding how the cell works as a mathematical system, just as we understand the universe by studying the mathematics through astronomy. And in fact, many of the scientists who are in astronomy are coming into our area. And this gives us the precision now to be able to be applied, not only in terms of illness, but we can study wellness. which is extraordinary, really. We can actually study the biology of wellness as well as illness, and, of course, demystify diseases like chronic fatigue syndrome. So we're living really in a sort of a different revolution now, where pathology is not driving the interests. It's understanding the biology of complexity. And it's been given different names. I rather like this one, the living systems revolution. That we're interrogating the constant buzz of information transfer that's going round cells to find out what's going wrong with them in human disease. And I put this diagram up. On the right-hand side here, sorry, the left-hand side, we've got a fungal cell, one cell from a fungus. And one stimulus has been given to that cell, as you can see at the top. One chemical stimulus has been given. And these are all the different pathways that are activated as a result of that one single exposure to one chemical. If that same chemical is put on a human kidney cell, that's the complexity we get. So now you can see we're not living in a linear world of cause and effect. How can you interrogate that intelligently without understanding the interactions of all these different molecules? And even between organs, this is happening. So now, even in my own area where we thought asthma was a disease of the lung, we know it involves the bone and the muscle and all sorts of other tissues. There are these amazing organ connections too. So this now brings me to the end of my talk, which is about where we are with this condition. And I hope I've set the scene now to give you a paradigm shift of the way we want to go with this. Because this, as many of you will have seen on the internet, is the sort of wordle that comes out of this condition. And in that is captured the patient experiences, which are highly complex, very much fitting that model of a single stimulus causing all those multiple effects. Very much sitting in that area. It's not a single disease, it's a complex series of diseases. And that's why our treatments really are not making any progress at the moment, because we don't know what these different pathways are. And we've got to unravel this. We've got to use the technology to get to grips with the underlying driving processes, which are going to be multiple and different in different people. So, this was the reason why I got out of my lung domain and into this one, because I honestly felt that this was the time to start grappling with this difficult situation. We've got a common disease. It's one with multiple causative pathway. We've got the disagreement over mechanisms. We can't even agree over how we characterize the disease and define it, let alone understand mechanisms. We've got very few treatments. The quality of research is variable and poor on the whole. There's a breakdown of trust between patients, scientists and clinicians, and we've got hardly any funding. So that's not a great sort of, thing, is it really? But, can we change this? Of course we can change it, because the area now that we want to be able to move in is to build a new way of looking at this group of conditions. And it was started by the MRC 4 or 5 years ago when I was asked to chair a small group to get something going, and we gave a few grants out, and that increased the confidence that we could do it and get high-quality research moving. And you're going to hear about now, over the next hour or two, and about the large collections of patients, the biobanks, the various physiological collections that are being used, the different methods now that are being applied to these biobanks, which I've talked about. You're going to hear about the potential of parallels in this condition with other human diseases, particularly the role of viral infections and molecules that are involved in that, and exciting work looking at the biology of fatigue and understanding what that's all about. We've got critical scientists coming out of other areas of science now into this area, which was desperately needed. So we've got the mathematicians, we've got the physiologists, we've got the biologists coming in and studying this group of conditions. And we've got, of course, the need for collaboration. And we need collaboration because we're not going to be able to tackle this on our own. We need everybody to come behind the efforts that are going to be made. Because this P4 medicine is all about putting the individual patient at the centre of understanding the disease mechanism. And we've got to understand the biological mechanisms They're sometimes called endotypes, which is the mechanism that's driving the different disease processes. So I think there's strength working together, and we need a joined-up approach, we need to prioritise our research activity, and we need to build capacity with young researchers, bringing them out of different areas of science to do this. Will it work? Well, I don't know whether it will work, but we're not working at the moment, so anything's better than nothing. And a few years ago, when I set about doing this in the lung, it's been spectacularly successful. So this was the collaborative I set up in lung disease in 2005. Different organisations coming together in that circle there. I won't go through them all. And then funding bodies and various other organisations joining with us in this. What did that do? Well, it dramatically increased funding of research, for a start. I've got 2007 on this graph. We're now in 2013. The current grants are somewhere in the region of £14.6 million a year, so we're somewhere just up at the top end there. But that's about a 5-fold increase in research funding coming from the Medical Research Council, okay, not charities or anywhere else. A major change. And I go around the UK now and I see all these wonderful people doing this great work in mesothelioma and lung cancer and chronic obstructive pulmonary disease and cystic fibrosis, and it's really, really exciting. Well, some of you in this room were there on April the 22nd when we launched this collaborative. Shown there are the universities who came along and presented their science, some of whom are here today. Very exciting buzz. Fantastic feeling of optimism that we were able to do it if we work together. That's the objective of the collaborative. High level, not detailed. And of course, it enables us to begin to roll out, as I'm listing here, what's needed to make this work. And we have to now work together to be able to produce these different activities through this collaborative, which I'm very pleased to say this charity is a major driver as part of this. Now, we've only just started. This is the beginning, but we've started. And I can tell you, sitting on the executive of this collaborative, we've got some of the best scientists in the country working. Julia is one of them. But we've got the chair of the Neurosciences Board at the Medical Research Council. We've got the chair of the Infections and Immunity Board. We've got people from Bristol who are working on genetics, such as Esther Crawley. We've got the most amazing people now in science who are joining us. And they're not in MS, in ME, chronic fatigue syndrome. Many of them have come out of it, out of different areas, so they're coming from a different field. What we want to do is to raise funding, and we're going to hear a bit about priorities that this charity is doing. We want to raise awareness and publicity, not around the silly science, as I call it, but the serious stuff, the really important stuff. We want to get youngsters to go in and train in this area and, move the area forward. And we want to get lots of people interested in it. Patients, of course, being really important. So we're going to have an annual conference next September, and you'll be hearing more about that, where science is going to be what it's all about. And in that conference, we're going to have half a day where patients are going to come along, we hope, and we're going to have a proper discussion with them about how we should work together. And of course, we want a membership, therefore, that's not only just scientists, but we want people interested who are working with us. And we've got two different sorts of membership in our particular group. So I'll end, really, at this point, and just to say that I think we're at the beginning of an extraordinary journey, and I don't see any country in the world being where we are right now, honestly. I think that by coming together as a group, we can genuinely make a difference. We can build research capacity second to none, and we can then, of course, engage and strengthen the scientific basis upon which new discoveries will lead to new treatments. Thank you very much.